let's talk about something that is a genuine game changer. A new technology that could basically make massive power outages a thing of the past. Seriously. We're going to dive into how making our power grid a little bit smarter, actually a lot smarter, is making it unbelievably more reliable. You know the feeling, right? The power goes out, and you find out it was because a single tree branch fell on a wire, like miles away, and it took out your whole neighborhood. It feels kind of crazy, doesn't it? Well, there's a reason our grid is set up that way. It all comes down to how it protects itself, and a really fundamental problem in its design that we're only just now starting to solve. Okay, so first things first, let's really nail down the core problem we're trying to fix. If you want to make blackouts smaller, you have to find a way to shrink the area that gets cut off when something goes wrong. Now, the solution seems pretty straightforward, right? You just install more of these automated switches out on the power lines. You take one huge power zone and just slice it up into a bunch of smaller ones. That way, if a tree falls in one little section, it only affects those few houses. Problem solved, right? Well, not so fast. This is where things get really, really interesting, because that simple, common sense solution slams headfirst into a huge, hidden problem. You see, for decades, our entire power grid has been coordinated using, believe it or not, what are basically just staggered countdown clocks. And this right here shows you exactly what I mean. Think of these curves as timers. On the left, with just a few devices, you can have these big, safe time gaps between them. It's all set up so the switch closest to the problem trips first. But look what happens on the right. When you start cramming more and more devices onto the line, those time gaps get squeezed and squeezed until they're dangerously close. One tiny hiccup and the wrong switch trips, causing an even bigger blackout than you would have had before. It is a total coordination nightmare. So if the clocks are the problem, how do you fix it? Well, you do the radical thing. You just get rid of the clocks entirely. Instead of having all these devices trying to guess where a fault is based on these delicate, staggered delays, what if you just let them talk to each other in real time? And what you get is this. This graph shows the result, and honestly, it looks impossible. With a communication system, every single device on the line can be set to the exact same super fast response time. Now, based on everything we just said, that should cause absolute chaos. So how on earth is this possible? The secret is an idea that is so simple, it's brilliant. We can call it the one-block rule, and it is the absolute heart of this new technology called high-density coordination. So what is this high-density coordination, or HDC, anyway? Put simply, it's a system where all those protective switches are using high-speed radios to constantly talk to one another. They stop guessing with timers, and they start working together to figure out exactly where a problem is, and they isolate it instantly. Okay, here's how it works in practice. A fault happens, say a tree hits a line. Every device that can see that fault immediately sends out a block signal to its neighbors. It's basically shouting, hey, I see a problem over here. Now look closely at device R2 in this diagram. It gets a block signal from its upstream neighbor, R1, but it hears nothing from its downstream neighbor. And that silence is everything. Getting only that one block signal tells R2, the problem is right next to you. You're the one. It's your job to open up. So let's just walk through that logic one more time because it's so elegant. Step 1, fault happens. Step 2, every device that sees it sends out a block signal. Step 3, each device simply counts how many block signals it's getting. And step 4 is the key. If a device gets 2 blocks, one from upstream, one from downstream, it knows the fault is somewhere else, so it stays put. But if it only gets 1 block signal, it knows it's the gatekeeper for that fault, and it trips. It's that simple, and it happens in milliseconds. Now, this all sounds amazing on paper, but does it actually work when the rubber meets the road? Well, let's take a look at a fantastic case study from Alabama Power to see how this thing actually performed in the wild. So here was the situation. They had this one main power line, a feeder, that was serving almost 2,000 customers. And it was only broken up into 2 big zones, protected by just 2 of these automated switches. This meant that any problem anywhere along that long line was going to cause a really big outage. And this is the money shot. This shows you just how powerful this idea is. On the left, you see the before scenario. In the old world, a fault at that location would have knocked out power for 237 customers. Now, on the right is what actually happened after they installed the new HDC system. The same fault happened, but this time, the grid surgically isolated it, and only 2 customers lost power, from 237 down to 2. Let's put some hard numbers to that. Utilities measure the impact of an outage in something called customer minutes of interruption, or CMI. It's just the number of customers out multiplied by how many minutes they're out for. For this event, under the old system, the CMI would have been a staggering 95,274. And with the new HDC system in place, the actual real-world CMI for that event was just 804. That is a 99.2% reduction in the impact to customers. I mean, think about that. This isn't just a small improvement. It's a complete paradigm shift. I know. Numbers that good can seem almost too good to be true. So you know what? Let's look at the receipts. Let's look at the actual data that the devices recorded millisecond by millisecond during the event. So this is the data log from device R14, the one that was right next to the fault. You can see the exact moment the current goes crazy. The device sees it, it sends its block signal upstream, and then it waits and listens. And because it heard nothing but silence from its downstream neighbor, it knew it was the one. And there it is, right there. The HDC_trip signal fires in just 58 milliseconds. It's a perfect textbook operation happening faster than the blink of an eye. So, let's zoom out. What's the really big picture here? What does all of this mean for the future of the power grid that we all depend on every single day? Look, the takeaways are just huge. This tech shrinks blackouts, which means a way more reliable grid for all of us. It lets the power companies chop the grid into tiny little pieces without all those old timing headaches. And because it's all based on communication, the system is smart. It can automatically adapt if power gets rerouted for some reason. This really is the blueprint for the smart grid we've been hearing about for years. Ultimately, this is about way more than just keeping our lights on. It's about building intelligent, resilient infrastructure that can literally diagnose and fix its own problems in an instant. So the question I want to leave you with is this. If our power grid can learn to talk to itself to prevent blackouts, what other important conversations should our infrastructure be having?